Hi everyone, my name is Huang and I am currently an undergraduate student at UCLA working at HiLab. I'm thrilled to be presenting our new work, WheelPose, Data Synthesis Techniques to Improve Pose Estimation in Wheelchair Users, done in collaboration with Sam Ghahremani, Siyou, and my advisor, Zhang. Given the recent popularity of deep learning models in everyday technologies, it has become increasingly important to address potential disparities in their performance. One key factor in this problem is the diversity and representation of the underlying training data, which is directly correlated with the amount of bias in the resulting model prediction. For this work, we focus on pose estimation AI models. Most of the commonly available pose estimation models are trained from a set of publicly available human posture datasets. As shown in a prior work surveying existing posture datasets visualized here, most of these datasets contain little to no data on people with movement impairing conditions or disabilities. This lack of representation in training data directly affects the quality of posture predictions. We see that popular pose estimation models like Detectron 2 fail to accurately predict the posture of wheelchair users in everyday situations. As shown here, these models often mistake parts of the wheelchair as a limb or even completely miss certain joints. Much like how synthetic rubber was developed in part because of concerns over the availability of natural rubber, we propose a new approach to this data problem, synthetic data. While traditional motion capture is limited by the accessibility of the environment and the feasibility of the motion itself, synthetic data can supplement insufficient data collection without being limited by physical constraints. One key advantage to synthetic data is in its modularity and customizability. While real-world data capture lies on a spectrum of difficulty, like how some motions are more difficult to perform than others, synthetic data enables us to simulate environments and motions without any sacrifice in feasibility. This idea is the driving force behind our data generation pipeline. Our pipeline allows developers to enter their own motion data, environment data, and simulation configurations to easily generate large amounts of synthetic data of people in wheelchairs. This data can then be directly used to fine-tune existing pose estimation models to improve their performance when tested on users in wheelchairs. All user-defined parameters are compiled into a Unity-based simulation engine. For each image, virtual models are randomly placed and rotated in the camera's view. For reference, the camera is the collection of 3 arrows in the middle of the screen. Each avatar can be configured to have a completely unique physical appearance based on the user-defined age ranges, clothing options, and wheelchair type. A background image is then used to set the environment of the simulation. Randomized occluding objects like the small cubes and cylinders floating around the screen are placed to simulate natural amounts of object occlusion that we see in real data. Finally, the general lighting and camera configurations are randomized to create further diversity in the generated synthetic data. The time of day, point lights, camera intrinsic parameters, and camera position are completely unique per image captured. More information on our data simulation engine can be found in our paper. The underlying simulation engine will then capture joint-accurate ground truth data on posture, bounding boxes, depth imaging, and image segmentation. While these simulations are relatively rudimentary and unrealistic, we still find noticeable improvements in pose estimation model performance as seen further on in the presentation. Given the near infinite amount of possible configurations, we first set out to address how to generate synthetic data that is effective in improving pose estimation models. We do so by evaluating the efficacy of different motions, environments, and simulation configurations. We analyzed 2 primary sources for motion data: real-world motion capture from the human ML3D dataset, and AI-generated motions from the text-to-motion motion generation model. These sources were selected to investigate the impact of sourcing real motion data compared to generative AI outputs. Furthermore, the ability to input AI-generated motion data can enable a far higher degree of variability and customizability in generated motions that are not limited by whether a motion has been defined in an existing dataset. We do note that most motion datasets and related AI models focus on fully able-bodied users. Thus, in our motion generation process, we take the upper body movements of the inputted motions and synthesize the lower body movements to align each motion with the wheelchair in our simulation engine. During our fitting process, we also add a degree of smooth random noise to the lower body to simulate the regular movements a user might have while in a wheelchair. We acknowledge that the fit of the legs onto a wheelchair is not necessarily a fully realistic representation of someone with a disability and believe that more work can be done to more realistically simulate motions from users with disabilities. Given both the fact that we are using motions generated from an AI model and the limitations of our pose modification process, we conducted some further investigations into the realism of our tested motion data before proceeding with any further testing. We developed a web UI to conduct a survey study asking participants to rate the ease and frequency of each AI-generated motion on a 1 through 7 Likert scale. Motions were displayed on a skeletal model to better embody the individual user and focus on the general realism of the motion itself. Evaluators were also asked whether or not they had already seen this motion in their daily life. 13 evaluators with varying levels of spinal cord injuries, or SCI, from the wheelchair community participated in our online study. Evaluators had varying activity levels and occupations, which could affect their perception of different displayed motions. More information on this work can be found in our paper. From our survey study, we found that most motions were rated as frequently seen and easy to perform. Given that the higher the number, the more frequent or easy, most motions in both motion capture and AI-generated datasets fell above a 4 in both categories. Contrary to what we might expect, we also found that the AI-generated motions tended to be perceived as more frequent and easy when compared to its real-world counterparts. This indicates that the potential for AI-generated motions to be used as an alternative to traditional motion capture given its ease of use and practicality. We found that frequency and ease were also highly correlated, which is supported by user testimony that harder motions are often circumvented with easier ones when possible. Much like our selection between motion capture and AI movement data, we also tested the use of 3 different background image sources for use in our simulation. These images create the environment in our simulation engine and provide the backdrop for the virtual users in wheelchairs. We selected 3 different background image sources: real-world images from the BG20K dataset, synthetically generated data from the Unity Synthetic Homes data generator, and random textures from the Unity Perception package. Examples of each image from each source are shown here. These 3 sources provide a range of images with varying degrees of realism to allow us to analyze the impacts of environmental realism on synthetic data performance. Finally, we tested the configuration of the virtual model's appearance in our simulation engine. While other simulation settings are configurable, we choose to focus on the virtual model's appearance to analyze the degree of information transfer between virtual and real humans in pose estimation models. Using the Unity Perception package, we tested 2 possible configurations for the model: a default Unity humanoid with no variation, and a collection of synthetic humans with unique physical appearances, size, and clothing like the ones shown here. We evaluate the efficacy of individual configuration options to identify an optimal synthetic dataset through a series of ablation tests where we generated datasets with only one parameter change compared to a base. Each dataset was generated with 70,000 captured images and used to fine-tune the Detectron-2 pose estimation model. We used the mean average precision, or MAP metric, a measure of a pose estimation model's performance where higher is better. BB indicates bounding box performance, which quantifies the model's ability to detect a person. KP indicates key point performance, which quantifies the model's ability to identify a posture. More information on our testing procedure can be found in our paper. Through our testing, we identified that the use of AI-generated or synthetic data parameters not only had little adverse effect on the performance of the generated dataset, but even outperformed real-world data in certain scenarios. We also added a new AI-generated motion dataset, which had the bottom 10% of combined ease and frequency evaluation scores removed to find even greater improvements in performance. From the results of our ablation test, we then assembled WheelPose Optimal, a dataset generated from the best performing parameters found from ablation testing, which include AI-generated motions with the human evaluation metric, synthetic backgrounds, and synthetic human models. This dataset is used to evaluate the efficacy of using synthetic data to fine-tune existing pose estimation models and improve performance. We first analyzed the human detection problem by analyzing the bounding box performance of Detectron 2 fine-tuned with WheelPose Optimal compared to the bounding box performance of Detectron 2 ImageNet, the baseline model, on users in wheelchairs. We also tested the performance of Detectron 2 fine-tuned on People Sans People, or PSP, an able-bodied synthetic dataset to provide another baseline comparison. The same evaluation metrics of average precision was used with different IOU and size levels indicating the performance of our model at different depths from the camera. Further information on our testing can be found in our paper. We fine-tuned Detectron 2 on 3 separate seeds using a synthetic dataset of 70,000 images to find a near 100% improvement in bounding box performance. This indicates that Detectron 2 recognizes our virtual models as similar enough to real humans to enable a high degree of information transfer across mediums. A similar trend is seen in key point detection performance, with a 7.6% improvement in key point mean average precision over the base Detectron 2 model. Here we show some examples of our improved performance. Seen in green is the prediction from Detectron 2 fine-tuned with WheelPose Optimal, and in red is the baseline Detectron 2 ImageNet. We find that when fine-tuned, the model is able to recognize occluded legs from the wheelchair position. We also find that the bounding box encompasses more of the user's body, especially important as users in wheelchairs often regard their wheelchair as a part of the whole. We see a similar trend here, where our fine-tuned model is able to discern where the user's legs are instead of mistaking the wheelchair's wheels as legs, a common problem in existing pose estimation models. Shown here is an example of improved wheelchair user detection. In low visibility scenarios, we find that our fine-tuned model is still able to recognize the user in a wheelchair and accurately assign a bounding box, while the baseline model cannot. While our model shows great promise, we also note that our approach can result in a high degree of overfitting, which can diminish the pose estimation performance in certain situations. Since we did not consider the situation where the user may lack a limb, we find that our fine-tuned model can overfit and assume a limb where there are not any. This problem is indicative of a larger scale issue in pose estimation where current data formats and training are not equipped to identify someone who may not have a certain limb, often choosing to label the joint as occluded or not in view. Furthermore, we find that our model can tend to overfit to simply the presence of a wheelchair. In this image, the model predicts a full human skeleton onto an empty wheelchair. WheelPose was designed with extendability in mind. Thus, we choose to base our work in Unity to enable developers to continue testing our approach in other disabilities that extend beyond users in wheelchairs. We believe our work offers a unique approach to making vision AI models more fair and equitable that could be potentially extended to other models in the future. Furthermore, our ablation testing also creates new questions on the effects of realism and information transfer between synthetic data and AI models. We believe future research analyzing how much realism is necessary can provide vital information into creating synthetic data generators that are both effective and easily scalable for developers regardless of their access to computing power. Finally, our human evaluations also lead to new questions into how users with disabilities can be integrated into the pipeline through an iterative human-in-the-loop process to create more effective and personalized synthetic data. In the spirit of our work to improve equitability, we have also open-sourced all our code and welcome developers to contribute and test our system further. Thanks for listening, and please refer to our paper for any more details. Happy to take any questions.